All right. Hello, everybody. This is Josh Nearly. I'm here with Lee Elberson. Um, we are going to discuss everything you could ever want to know about physics in about an hour. Is that right, Lee? Is that what we're doing?
You might be giving us a little bit too much credit. I would say half of everything you wanted to know in an hour.
Okay. Okay. That's not too bad. Half of everything. So before we get into that, we just kind of want to set up. We're looking to do at least a three-part series on some really fascinating concepts that I've found. And Lee, well, actually, how about this? Let's start with this. Lee, why don't you give us a quick introduction of yourself and why you are the expert of experts in physics?
Okay. Well, this is great. This is why I wanted to do my own introductions. I am not claiming to be an expert. I am just claiming to be passionate about it. I've always been curious. I've taken apart just about everything I've ever owned just because out of curiosity. And that sort of naturally led me into physics as an undergraduate at University of Louisiana. I went on to study atomic physics at University of Maryland for a couple of years as I was getting my master's. And then as I was on my PhD track, I spent time at Lawrence Livermore National Lab, um, basically trying to make small stars with big lasers. And that falls under the field of plasma physics. And so I've always had an interest in these things. And so my expertise would be very closely narrowed into laser fusion experiments, but I know enough about other areas of physics, probably just enough to be dangerous. And so I will say I don't know, but I always love to speculate about what I do know. So hopefully, if people
Yeah.
want to correct me, always open to that. So
And I think that, I mean, that's a great way to start this off too, because even if you are, I mean, even if you are, and oh wait, it says my recording has stopped. Dang it! All right,
I
you're gonna
got
keep
mine's
going.
recording.
All right,
Yeah.
whatever. Anyways, guys, you'll find that out later on. So even if even if you are an expert, it does, I think, always help to at least listen to everybody with a grain of salt. Now, there are people who know tons about physics, but they don't know everything, and that's the whole joy of learning. Like, you should ask questions, and you should be allowed to speculate on some level. I think that's the whole point of living. You don't want to know everything; that would be boring. Um, so great. Okay, I will. Well, then I'll lay
And
my
honestly,
cards.
even what is the concept of to know something? Maybe that's, well,
Yeah.
we could go off on a whole nother tangent of that, right?
Well, yeah, I don't even know if we'd ever get started on physics if we start with what it is to know. We just have to, well, I mean, we'll go over this in a moment, but there's like almost an infinite amount of assumptions that you have to start with just to wake up in the morning, I think, which we just accept as true anyways. All right, that is a completely other topic. That'd actually be fun to talk about. So I'll lay my cards out on the table. I know maybe like this much about physics, not very much at all, but it's always fascinated me, and I'm looking forward to understanding more about it. Okay, so one thing to note, some of you will be listening or watching this on my Why Would I podcast or YouTube channel. And for those who are listening to that, we do have a shared history. Um, I used to host it with James. I still will host it with him, but for those who don't know, he's going to get married here in August. So he's in the throes of trying to organize a wedding during a global pandemic, moving bookshelves from here to Lexington. So he's just not going to be as available anymore. And that's allowed me to strike off on my own and try new things. And I'm really excited to start this series, which will hopefully be about, I mean, maybe three, but hopefully more if the interest is there. So Lee, did you want to quickly walk us through what we're planning on doing for the format of this series?
Yeah. So as Josh said, we're both very fascinated with physics, and the objective really is to take very complex topics and discuss them in meaningful and fun ways. And we thought an interesting way to do that would be to run through a series of topics, release the podcast, give our listeners or viewers maybe a couple weeks to digest it, and then we're going to hold a YouTube live where you can chime in and just ask any questions you want. You can call us out on stuff that you thought was wrong about the podcast. Really sort of an open forum for us to discuss the topic again. And so we'll, let you know what the timelines are, and we'll probably include a YouTube live link in the podcast so that you can join in 1 to 2 weeks to discuss.
Yeah, which I think is a great idea because that way people have time to think about these topics that we've covered in more detail. And yes, like you mentioned, like please come with criticisms or questions of things we may have missed because we're just two people and we're going to miss a ton of things. Um, so, okay, so let's move on to the beginning of our discussion, unless you have anything else to mention, Lee.
I think that's it.
Okay, so we wanted to start off with the objective of science in the first place because it is quite specific in what science is aiming to do. So I'm going to let Lee do that in a moment, but I'll just say that starting out, I like to, this sounds weird, but I like to think of myself, I guess you would call it a Renaissance man. It sounds kind of cheesy, but I like to take certain topics and see if they connect to something completely random way over here. So if I come in at a left field at any point and start mentioning things about psychology or something like that, don't take me too seriously. I just like to throw those things out there because I do suspect in the end there's some underlying similarities between the universe itself and the human mind and how we perceive the world. And I would think there would have to be if we are a product of the universe, if that makes sense. One other thing I'll throw out there is I am a Christian, and so that part will probably come into play. I'll have maybe some minor critiques from time to time of physics or of science. And again, I don't mean that in any negative form. I think it does help to create some dimensionality to these studies. But if it comes up, that's the only reason I'm doing it, just curiosity. So, Lee, did you want to take it from there and then maybe introduce us with the objective of science?
Yeah, sure. And I think, you pointed out, I think there's some really interesting things about what you discussed. And a younger, more arrogant physicist in me would say that if you knew all the physics in the world, you could deduce all the other sciences. I'm not quite that arrogant anymore, but there is still part of me that thinks that it really truly is just a combination of fundamental forces and atoms. And if you know specifically that, you could deduce all the other sciences.
Well,
When you get to psychology and biology, you have to, just like you said, you have to start with bigger and bigger assumptions. And the reality is you don't want to wait till physicists have figured it all out, because we we don't know when that'll be. And so you have to start from somewhere. And so that's why we scale the varying levels of science.
yeah, I like that.
And
Well, sorry, real quick. Like you mentioned, if that is true, that everything can be explained through physics, I do think that's at least, I mean, that certainly should be explored, right? Like if that is true, humanity should be trying to get to the bottom of that with all haste. But like you mentioned, I think in the meantime, I'll kind of come, like I'll never be a physics expert. I'm never going to discover a theory of everything through physics. So I'll have other fields of avenues of thought that I think could also help too. So sorry, keep going.
Yeah, sure. So it's definitely important to understand that the objective of science is to just observe the natural world and discover patterns and try to make useful predictions through theories and laws. It's really it. And what we observe and what we make into a theory and even to a law, those can be discovered to either be incomplete or to not be correct, and we find a more complete or more accurate theory. But that's really all it is. It is by no means meant to describe myth or belief systems. Politics is probably a perfect example. We don't want to try to apply the scientific method to what works in politics. So that's essentially what we're trying to do. Is we're just trying to look at what happens in the natural world and be able to make some useful predictions.
Quick question there. So science relatively, I mean, I guess theoretically it's relatively recent phenomenon in terms of this particular objective. What would you say was like the first modern scientific theory? Was it Newton? Was it before that?
Oh, definitely before that.
Yeah. Bacon?
Yeah, I mean, gosh, I'm not a scientific historian. Obviously,
Sure.
Yeah, I'm not. I honestly don't know what is established to be the first theory. When you think of Darwin's theory of evolution. You think about Isaac Newton coming up with this theory of this force that pulls us down to this flat object that we thought, now we know it's a curved object. I think those are the ones that stick out. But he's probably just very early on, somebody said, if I dump water at the top of this thing, it'll always come down to the bottom of this thing. Or, if I push against this, it'll push back against me. So I'm sure in someone's mind, very early on in the sort of cognitive revolution of Homo sapiens, somebody came up with what we would classify as a theory. They just didn't document it. So
Yeah, and I think, I mean, again, we'll briefly cover this and then move on to the next part. But I think in some ways, like for instance, the ancient Greeks came up with certain theories about existence, but it was purely through philosophy, right? So, I mean, Aristotle certainly attempted to observe the natural world in methodical ways. And so did many other cultures. The thing was, it was always within the scope of, well, I guess we'd call it now religion, but maybe spirituality would be a better way to describe it. So perhaps the modern science was one of the first attempts to like step outside ourselves, if that makes sense, to like separate ourselves from ourselves to observe the world. That's just a theory that I have, but if you want
I
me to,
think
yeah, go ahead.
that's, I was going to say, I think early on, religion helped Homo sapiens in a way to say, hey, look, there's all these things we don't understand. This lightning coming from above, this is, maybe some religions might say, oh, you're getting punished. And so that was a way for us to frame our not knowing about what's going on in the world. And then science came up with an explanation for that. And now, you sort of open Pandora's box, and there's so many things that you can't explain. The theories aren't fully understood or explainable. And so I think it's interesting that, in many ways, I think that's when you see this tension between religion and science, is because science came to explain some of the things that religion sort of grouped in and said, oh, this is a deity doing this. And we said, well, actually, this is just gravity. And again, just sort of deconstructing those and saying, this is gravity doing this, and it's somewhat irrespective of your belief system in a God. You can still always supersede these the science with some sort of belief system, if you wish.
Yeah, and I think, I think that the main problem with religion during those days was they became too ideologically driven, if that makes sense. So they were too held to one aspect of their belief in God, which was that maybe God, maybe God was the force that caused things to fall all the time. But I mean, again, I would just say, like, I don't see a contradiction between describing like how God makes things fall all the time, if that makes sense, through physics. And but you're right. There was a huge split, which at this point might be too late to reconcile. But it is helpful to know that there was a huge split, and but it does help to know, no matter what belief you have, like you mentioned, it doesn't really matter in a way, because science is used to describe the world. And as long as you accept those initial assumptions as a way to describe the world, there's a lot of fascinating things that can be discovered.
Absolutely.
So, speaking of fascinating things to be discovered, why don't we start with some fundamental forces of the universe? Fundamental forces, what does that even mean?
Okay, so what we're trying to do is we actually haven't framed what the topic of this conversation is. So this topic is, Josh is very fascinated with gravitational singularities, otherwise known as black holes. And so we're gonna frame this in a way that we understand how black holes came to be, and also it'll frame the rest of our conversations. So understanding fundamental forces and particles that drive those is important, because it helps us understand the natural world. So I usually like to think about it from what is considered the strongest force, and that is the strong nuclear force. There's two types of nuclear forces, so let's just call them the nuclear force. This is basically what binds quarks and protons together. And in some ways, the strength is important because it has to overcome what we know is the electromagnetic force, which is slightly weaker. The electromagnetic force is what dictates what happens between electrically charged particles, and also what dictates light propagation or some sort of irradiation.
Quick question.
Yeah.
So how do, let's just say, these two forces generally interact with each other? Is it that the nuclear force, it holds the particles together, and then the electromagnetic force holds the, well, actually, I don't even know. How do these usually interact with each
Yeah.
other?
So it's interesting in thinking about it because, if you think about the electromagnetic force is something that most of us have been taught, and that is that opposite charges, opposites attract and like charges repel. So naturally you'd want to think, okay, well, so then what keeps like why do protons all cling together in a nucleus? And that's because some of these forces have different ranges than others. And so
What is that?
different
What are
strengths and
range?
different ranges. So the strength is probably the first thing.
Okay.
Particles stay together because there's a higher strength of keeping a nucleus together than them being pushed apart by electromagnetic force. And then there's ranges. So ranges is, probably the easiest way to think about it is you have two forces, and we didn't get to the last force. So we talked about the strong and weak nuclear forces, those two of them. The third we talked about is electromagnetic force, and the fourth is the gravitational force. The gravitational force and the electromagnetic force are two forces that can theoretically have an infinite range. That means that an object on one side of the universe will feel the gravitational pull from an object on the other side of the universe. Similarly, a charged particle on one side of the universe would feel a charged particle on the other side of the universe if there was nothing in between them, if they were the only two objects in the universe. Obviously, once you have more particles, you get these things called shielding effects, which sort of limit the effective range of those forces.
So by an infinite range for these two things, could you also say that they are sort of inextricably linked to each other? If one particle on one side of the universe would always feel the particle on the other side, then there's no way that they could ever be truly separated, if that makes sense?
Yeah, it really brings up the concept of what physicists assume many times is assume this particle is by itself in a vacuum, right? Like you
Right.
discuss, oh, here's how this thing will act. And then you think, oh, well, what if there's two particles? How do they interact? Like here's an equation that dictates these two particles. Oh, well, now when you get three particles, it's like, oh, actually the equations get a little bit more complicated. Well, what if you have a billion, 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 billion of them? Okay.
Yeah.
Well, we don't have an equation that we can easily solve for that. So this is where simulations come in.
Okay. Yeah, I mean, it's similar somewhat to, I've always found it humorous in economics where you have to take the assumption that humans are rational actors, which, again, if you make that assumption, then economics makes a lot of sense. Um, but that's a big assumption I always find. So it is interesting that, yeah, you're trying to do billion, billion, billion particles interacting with each other. There's no way. You got to start from the bottom and work your way up on that.
Yeah, there's an old physics bit that starts with assume you start with a spherical cow. I don't actually know the origin of it, but it's a lot of physics jokes start with that.
Is that just like basically like assume you start with a paradox?
No, it's assume that like you have to start with you're talking about something and it's like, oh, it's a spherical, but it's a cow. And so like you're just taking things, you're just like talking about an approximation technique. And that's that physicists oversimplify things in order to come up with an equation for it. So that's probably a good segue into what we do and why you have to break things down to fundamental forces, because physics at its root studies the most fundamental particles, right? If we can, again, like I said, if you can understand how two quarks interact, quarks are what make up protons, then you could know how a proton could interact with an electron, which falls into the category of a lepton. And then you can say, oh, well, let's just keep adding more and more things, but you have to understand them at their fundamental. Now, that's not to
Gotcha.
say that there aren't other forces that you talk about. So people who take physics say, oh, what about frictional force? And what about this type of force? Most of the other forces that you talk about are some derivation of this. So a frictional force is essentially gravity causing some two objects to sort of press together, and what sort of cohesion do those two objects have once gravity's pressing against them? But so
But that's
most
still
things
under
fall
the
under these.
umbrella. That's still under the umbrella of gravitational force.
Yeah, the
Yep.
gravity comes out of the frictional force. Yeah.
So would you say that physics originally was meant, or at least the study of the universe and physics and motion, originally you wanted to find the smallest particle you could, and then from there now physicists are working their way back outwards to try and redescribe the world itself, because you can't, I mean, you can observe like gravity, but if you don't truly know what is at the fundamental like level, then you're never going to have a full understanding of gravity, if that makes sense. It's like an
Absolutely. It's
inversion.
like, well, like you started off saying, I mean, that you have to make a ton of assumptions, right? Like, think about when you try to come up with the theory of psychology, you have to assume that the neurons in somebody's brain work a certain way without, we don't, I mean, I can't give you an equation for how a neuron operates.
Yeah.
So I think that's you have to make certain assumptions, and so when you're at physics, you want to make as little assumptions as possible for your theory to be valid. And so if you
Al-
have the most fundamental particle, then you feel like you don't have to make as many assumptions.
Although again, I would say going to psychology there, like the assumption that neurons have to act a certain way, I think is already built on another assumption that consciousness is contained purely within materialistic universe, which again, you just have to take for granted and then work your way up from there. I'm a little unorthodox when it comes to that. I always think it doesn't make as much sense, but that's another topic for another
That's a
time.
whole nother, we could do a whole nother podcast on
We've got
is the amount of information in the universe finite? And if it is,
yeah.
then there is a series of equations that can dictate that. If it's infinite, then you can't, you'll always be approximating. But that is a different podcast.
I think by the end of this podcast, we'll have an infinite range of podcast topics. Maybe another fundamental force will be podcast topics at some point.
Perfect. So, I thought probably a good segue from this in terms of like talking specifically about black holes and gravitational singularities is to talk specifically about the gravitational force, because that's the force that everyone knows really well. Even from the point at which you're a child, you understand the concept of gravity. You drop something and it falls to the ground. Now, you may not realize that object, the earth is pulling on that object, and that object is also pulling on the earth. It's just that the earth is much bigger, and so this object proportionally doesn't move as much as the earth does. Sorry,
And
the object moves much more than the earth does.
oh, okay. So then would the earth, well, obviously then, yeah, that makes sense, because then the earth is moving much more than the sun does, right?
Yes.
Okay.
So it's a matter of scale.
Mm-hmm.
And so, I think something interesting to think of is how do rockets escape Earth? If gravity is always pulling back, we hear about rocket science, and there's all these anecdotes about rocket science being very hard, and not to say that it isn't. I've always thought of the space race and NASA putting together rockets is it's a much more of an engineering feat than a scientific feat. A really good example of that is, in order to calculate how fast you have to go to escape Earth, it's actually a very easy equation. It's just how much energy do you need to develop, in like kinetic energy is energy you get when you're moving, to overcome the gravitational potential energy. There's two variables essentially in the equation.
It,
Yeah.
I mean, it's fascinating there that you could, with the human mind, pretty much already know, like you said, rather simply, like how much it would take to go. So you can project your mind out into the universe and say, this is what we have. This would be the equation. But then to actually, like, in reality, like you said, with the engineers, to then accomplish what the mind has already thought of is a huge task. And that's kind of fascinating. I find that's often the case with these theories. Like the mind comes up with them first, and then in order for humans in reality and to get there, there's like a huge gap in between those two things.
Yeah, I mean, you think about like putting together the equation was relatively simple, but then putting it in context and saying, okay, you have to go 25,000 miles an hour to escape Earth's gravity. You think, okay, well, we can make a car that goes 200, so
Yeah.
we're
Yeah.
almost
Jeez.
1% of the way there. Interesting. I actually got to see a space shuttle launch in the 90s at Cape
Oh,
Canaveral.
wow.
As a night launch, and
Oh, wow.
it's a truly humbling experience. It lights up the sky like it's daytime, and you can feel it in your chest as these
What?
rocket engines are just blasting off. And when you think about the amount of power that it takes, and the fact that we did it with these, when during the space race, the Saturn V rocket was just this big fuel tank. It's 99% fuel and 1% people pod.
Yeah.
And you have
Yeah.
this thing that can generate, I think it's 1,000 times the thrust of a top fuel dragster. So a top fuel dragster, those things make like 2,000 horsepower. They go 0 to 60 in a second. And so thinking about something that's 1,000 times more powerful than that is it's an amazing engineering feat.
Do you remember what year that was that you saw the launch?
It was either 1996 or 1997. I remember it vividly because I wasn't a very good student. I'd skipped a lot of school in high school, and I calculated the maximum number of days I could skip. And the shuttle launch was at the end of the year, and I was thinking, "Uh-oh, problem. I don't have any days left," and so I didn't initially tell my parents. I told my dad that I didn't want to see a space shuttle launch, and he immediately was like, "What do you mean you don't want to see a space shuttle launch?" And I was like, "Yeah, I skipped too much school." So luckily, he went to bat for me, and they let me miss a few more days.
Wow. Well, it's funny when you were mentioning that, I just recalled a distant memory of when I was in elementary school, which must have been 96 or 7. We watched a launch on television, and then we all went outside and saw it. And we were in Virginia, so we still saw it, which was remarkable. So that, I mean, it might have been the same one. I don't know. That's kind of cool.
Yeah, I've traveled around, and I think I've seen all of the retired space shuttles. I think we've seen Atlantis, Discovery, Endeavour, and I think Enterprise. Enterprise and Endeavour are actually pretty close to Charlottesville. One of them's at Udvar-Hazy, and the other one's at the Air and Space Complex. One of them is in Houston or Florida, I can't remember, and then one of them's in San Diego.
So, okay, so rockets escaping the Earth, a good example of how humans can kind of overcome fundamental forces, or what would you say that's a good example of exactly?
I wouldn't say it's humans understanding the scale of fundamental forces. And it's interesting when you look at this chart, which you and I will include in the podcast later. The gravitational force is one of the weaker forces in terms of fundamental forces. But it really shows you the magnitude of what it's like to have something as massive as the Earth, and for a being like us to try to escape it. Either that, or it shows our limited technological knowledge, that we're using like fuel to power us off instead of some sort of electromagnetic booster or something, or anti-gravity machine. No.
So would it work?
you know
Would it work better to use either of those two because those types of forces have an infinite range? Does that have anything to do with it?
uh well, the issue really is that you're trying to overcome gravity, and you need some sort of propulsion
Hmm.
technique. And we don't we haven't found a way to really use the other forces as a way of propulsion, in the same way that we do burning fuels, basically.
Um, do you, do you think it was because nuclear force doesn't have an infinite range that we were able to harness that first? Does that have anything to do? Like, is it not more straightforward, but like more feasible?
No, I think it's just a
Okay.
matter of. I mean, I think it's more a matter of our evolution and the resources that we have. We discovered fire, and then we use that. Burning things as a propulsion technique has always been what we did. And so, if we were ever to discover an alien species, it's possible that they would have a different propulsion technique,
Yeah.
just because of the way they evolved. And if you have different resources, we just have a lot of these fossil fuels on our planet, and so we decide to use those.
What
But
what
yeah,
fo- sorry, what forces are used in fire? I don't fully understand fire. I know that sounds strange. Like what are there is it like a nuclear force, like electromagnetic, gravitation? Like how are we able to use fuel to move?
um, yeah. Well, uh, that's yeah, that's really just a matter of um creating thrust by burning something. You're actually not really using any of those forces. You're actually using more of a chemical process.
Oh,
So these fundamental forces, if this is why they do research in physics. If you were able to harness like a nuclear reaction, like nuclear propulsion is that you hear about in Star Trek and a lot of these
mm-hmm.
places. If you were to harness that, you wouldn't need a Saturn V, right? You could do it with a thimble, right? So we're not
Okay.
really able to harness that yet.
We're still in
There's
kind
all
of the
these.
we're still in the caveman stage of that. If we're still
Oh
using
gosh,
yeah,
yes. Now
yeah.
there's all these really crazy things, like warp drives. They call them, I think, albuquerque drives, where you essentially distort the gravitational space time, which is probably a good segue for us to get back on topic and talk about um, what is like who first really helped us understand gravity. And certainly Isaac Newton um, was the initial visionary for understanding the principles of gravity, but it was really Einstein who really just sort of blew our socks off um, when he came up with the general theory of relativity. So it probably is interesting to note that, like, in some ways Einstein's theory sort of disagreed with Newton's, but Einstein was always this master of these like thought experiments. He always had these like crazy experiments that he would think of that weren't very realistic but really framed very simple concepts. And so
Hmm.
many people have heard of special theory of relativity. Special theory of relativity, it was actually came out before the general theory. It came out in 1905. And
Hmm.
that's when Einstein essentially linked space and time together. Um,
Okay.
and it wasn't until a decade later in 1915 that he came up with the general theory of relativity, which basically introduced curvature of space-time and talked about how that's how objects stay in motion, and that's essentially what dictates our gravity. And you'll see a lot of 2D animations if you Google it on YouTube. You'll see like these trampoline effects where you have a really big ball and then the small ball goes towards it. That's important to keep in mind. That's a simplification because that's essentially taking a 2D analog. We have to remember that we live in 3D, so you have to imagine, if at all possible, that you have these 3D trampolines that are able to distort the space-time curvature in such a way that that objects are pulled together.
So with the uh, you said specific theory of relativity, is that what
The
they call it?
special theory of
Special, sorry.
relativity, yeah.
Um, so I guess the general theory was that then basically just to provide dimensionality to that original theory, like it stepped outside and added more dimensions to it in some ways, because like space time again, we basically just two dimensions there, right? And so you needed an expansion, perhaps. Is that a good way to think of it, or a
Yeah,
terrible way to think of it?
well, no, it's not. I think a better way to think about it is that special relativity was really designed. I mean, it helped us understand the principle of the speed of light, right? To understand that like there is some limit to how fast something can go in this universe, and it didn't really it didn't really cover what happens under the field of gravity. It happened like in a vacuum, imagining that there's no gravitational forces. So that's why Einstein felt like the special theory of relativity was incomplete, because it didn't include gravity, which just shows how something that is simple to us is actually a very complicated topic. Because what happens to a lot of these theories is, if you just observe something from your roof and you say, oh, I dropped it off my roof and I actually measured gravity pretty close. I measured it to about 9.8 meters per second, or 32 feet per second squared. And you say, okay, well, now I'm going to go do that at the top of Mount Everest. Assuming that you so maybe if somebody takes you up there in this special helicopter that can make it up to the top. And then you start performing these same experiments and you think, oh, actually, I'm starting to get a little bit different of a number. Now, let's say you try to do it on the surface of a neutron star. Now, let's say you try to do it at the surface of a black hole. Again, something that's just very dense. Then these theories really start to break down. And that's where we have trouble with a lot of physics theories, is when you look at extremes. Many of the theories are meant to cover what we see in our everyday life, and probably 99% of what we encounter. It's just, if they're not complete, usually it's a fault in the theory. The theory just is not perfectly explaining what happens in nature. It's not that, for the longest time they didn't think, oh, maybe black holes don't exist. This is just some theoretical construct. Now we know they do exist. Our theories just can't perfectly describe them.
Okay. So yeah, there's a good, I guess there's a good synergy between those two things. Like on one level, the mind, like with Einstein, can conceive of this theory of relativity, which is remarkable and like revolutionary. But on another level, like there are things out there that you haven't fully been able to conceive of through your mind. You might be able to glimpse it, I suppose, which is maybe what Einstein got. He got a glimpse of it, a brief moment of illumination, but that fades pretty quickly when you, like you said, when you try and go on Mount Everest, or then when you try and go out to a black hole from there. And I guess that's what I probably use dimensionality completely different than you would for physics. I've really come across that term recently, where I think if you just have, if we go back a bit to let's just go back a bit to everyday life. If you just have one belief or one worldview or one way of living life, and you just try and go throughout all of your life with that one dimension, it doesn't describe the world. So if you then have two beliefs that can then interact with each other and become more powerful, or more a better way to describe how you live, then you at least have a better understanding. Now, if you add in three, then suddenly it starts exponentially to grow. Now, I haven't fully developed that theory. I don't even know if it makes sense, but I do find it kind of helpful to think, like with Einstein, for instance, space-time was 2 dimensions, and then adding in gravity, you suddenly, like, everything expands to a lot more complex.
Yeah, no, I think it's adding another layer, right? In physics, the dimension is we observe 3 space dimensions, and 1 time dimension. And, sort of a foresight into where this podcast is headed is, at our last part of this 3-piece series, is we'll discuss string theory, which adds up to, I think, 27 space dimensions and 2 time dimensions. It's been a while since I've looked in it, but it's adding in more dimensions to this. But you're talking about like different layers. And so essentially, Einstein was always searching for the theory of everything, right? Like a theory that fully described our entire world. This is what a visionary he was. Interesting too, when he was discovering, or when he was publishing general theory of relativity, he also postulated this idea of a gravitational wave, which is really fascinating. It's basically like ripples in basically space. And it happens, it happens basically when like massive astronomical events happen. So like when a star explodes, or you have like black holes orbiting each other, they're basically rippling space-time, and those ripples will travel at the speed of light. This sounded, it was a completely insane theory. And, Einstein was criticized very harshly for that. And then lo and behold, at the Livingston interferometer gravitational observatory, they discovered it. I think it's probably been 15 or 20 years now that they've actually discovered a gravitational wave, proving that this is, it's just further proof that this theory holds water. But Einstein was just never happy with his theories. And
right.
One of the things he was never happy with is our second podcast. We're going to talk about quantum mechanics. Quantum mechanics and gravity, or in general, the theory of relativity, never really, they never truly meshed together. And this probably drove Einstein wild, right? He was just constantly trying to figure out how to marry these two.
Yeah, it's fascinating because there's a lot of similarities there. I don't know much about Newton, but like he ends up trying to find, like, to derive, like he was really into alchemy, right? So trying to derive gold from anything or whatever it was, which sounds insane, but in some ways it kind of, he lived in a different time, so Einstein didn't really have alchemy anymore, or like a more religious world, and so but he was still driven, like you said, like you're obsessed with trying to find, like, why aren't these things matching up? It doesn't make sense, which is really the joy of learning. Like, I find, now going back to the gravitational wave, I've never heard of that before. That's fascinating. If you go back to your thought experiment though, with the trampoline, it makes perfect sense. If you've ever been on a trampoline before and someone jumps in the middle and you're on the edge, or if you're closer to it, you're going to fly too. Like there are ripples that go out in a trampoline. I don't know if that makes sense or not, but
it does. Yeah. If you had it's, again, an Einstein thought experiment, if you had an infinite trampoline that was very taut, and you had two people sort of like bouncing on one side, they would essentially could create a ripple so big that you would feel it on the other side of the trampoline. So,
wow.
Anyway,
That's
I think
so cool.
it's probably about time for us to get into what you are fascinated about, Josh. So this is what came about, is you were asking about singularities, and I had to specify, are you talking about gravitational singularities, which is something I think is very fascinating, or technological singularities? The technological singularity.
If it's a true singularity, it's just going to be all of them, right? In the end? No, I'm just kidding. But yeah, no, yeah.
Could be, right. The one massive black hole is just going to consume everything.
Inside us and outside us.
Yeah. So I guess it's probably useful to discuss how we get to a black hole, right? So in terms of what happens astrologically, you have a bunch of matter in a stellar cloud, and that forms a star. Once you have a star essentially is an object that has a fusion reactor at the middle. So our sun, for instance, is a star, and it's undergoing fusion, which is the process of taking two nuclei and forming them together. And that takes a tremendous amount of energy to be able to push two nuclei together. So you could put two hydrogens together to make a helium. It's not usually that easy. Usually if you put two hydrogens together, those two nuclei will stay, and you'll just have two hydrogen atoms. To actually put them together is to sort of overcome some of those nuclear forces, and it takes an extreme amount of energy.
Oh. So is that the opposite of a hydrogen bomb then, when you split the hydrogen atom?
Yeah, you form and there you're forming usually a fission reaction where you're causing a chain reaction. It's still based on harnessing nuclear power. You're just forming a chain reaction where you have some sort of bomb that basically starts this chain reaction that starts sending out more and more power. It sends out X-rays and sometimes gamma rays, and it's
Remarkable.
really terrible. Yeah.
Yeah. Well, okay. So if is it that if you have enough mass, eventually this fusion will occur? Or how does the fusion first start? Do you know?
Well, the fusion first start. I mean, it once you get enough of these, once you get enough of these molecules or the nuclei together, there's a lot of pressure on them. So, as we know from the ideal gas law, pressure and temperature are related, and temperature is associated with energy. So, if you put enough energy into a system, you can form a fusion reaction. That's the idea of a lot of like laser fusion experiments. Is you're putting enough focusing enough energy that you're
Hmm.
forcing a fusion reaction to happen with a specific type of fuel.
Okay.
In a star, they've already got those conditions, but what stars have going for them is they're so large that by the time you get down to its core, the gravitational field at that point it's so strong that you have all this matter sort of pushing it together, that you have this rise in temperature. And
Hmm.
you can imagine that, let's say you're trying to push two really thick balloons together. You've got one in one hand, one in the other. Like they're going to squeeze around each other.
Hmm.
Well, imagine that you have a million of them. The balloons in the center of those, it's like you have a bunch of people pushing on them. The ones in the center don't have anywhere to go, right? So they're going to be forced to sort of break and push together.
Hmm.
Whereas what we do in labs is we only have a few of them, and so in order to try to create that symmetric process, that's our biggest problem. Is we can't keep it symmetric long enough that it just fizzles out. A star doesn't have that problem because
Hmm.
stars don't happen. I mean, we're making fusion reactions in labs
Yeah.
like within a billionth of a second. Stars have millions of tens or hundreds of millions of years to sort of form and create these very symmetric conditions. So that's what's happening. It's pushing all of the atoms together, and as this fusion reaction starts, as two atoms sort of fuse together, they release energy, right? This is why we bake out in the sun, right? You go out in the sun, it's just giving us energy. We haven't had to do anything. Nobody had to pull a pull start handle on it. It just goes, it just releases energy.
Yeah.
When you're really close to it, it's releasing really high energy waves like X-rays and gamma rays. And what happens is those will then collide with other atoms, and now they're energetic. And so then the fusion reaction starts happening more, and then hydrogen starts forming helium, helium starts forming lithium, beryllium, and then it sort of goes up the chain. And
Wow.
then as you have more and more mass, then what it's feeling at the core, then it starts getting pulled in more and more and more. And so at some point, it's pulled in, the energy is too high, and you'll usually have some sort of explosion. This is what a supernova is there's too much mass, and so the inside just explodes out. There's a
So
couple of different, yeah.
sorry. So the sun, like when a supernova occurs, is it that the sun has continued to acquire mass, or that the fusion itself is becoming more and more powerful and can't be contained?
If the sun doesn't acquire any more mass, it will never turn into a black hole. It has to have more. It has to acquire more mass, and this goes into the concept of
Hmm.
gravity, right? It's pulling objects to it, right? We don't really observe. We would never observe that in our time scales. Human beings don't live long enough to observe this sort of thing. But if you give a star millions of years, at some point a planet, asteroids are going to go into it, a planet is going to go into it. And you can imagine that under certain conditions, let's say initially two big stars actually collided to form an even bigger star. Then they're so massive, they're going to start pulling in, like the Earth would never be able to orbit if our sun was 10 times heavier, right? It would just fall into its orbit, kind of like a satellite that's not that doesn't have enough velocity to keep it orbiting around the planet. So
Yeah,
I
that's
guess the
fascinating.
sidebar is, yeah.
Sorry, I was going to say, like going back to that trampoline thought experiment, if you had two tiny little marbles on each end of the trampoline, nothing would really happen, right? But if you had a massive bowling ball, eventually it starts to bring everything together with it.
Yeah, and the way we get in stable orbits is, you can imagine that, like, you have those marbles. If you push it around fast enough, it's gonna keep going around that object fast enough. But if you push down harder on the trampoline, all of a sudden now it's not going
Mm,
fast enough to stay out of that orbit. And so
mm,
that's essentially what happens, is these stars get more and more objects, and you get this supernova explosion, which the physics of it, I'll be honest, it's been a while since I've studied it, but essentially it's just spitting out all of the mass of the star. However, that mass still exists, and so if the supernova, or the star before that, already had it's called the neutron star limit. It's basically the point at which there's so much mass that, like, it doesn't have enough energy. It can't blow it out fast enough that it's not going to get sucked back in. So
mm,
what happens is the core is actually starting to implode, and that mass
mm.
on the outside is destined to come back in. And so when an object, like, goes past that neutron star limit, it collapses into a black hole very fast. It's less than a second. So it's
Wow.
amazing if you were watching, like, a time lapse video, something that's like, let's watch this 10 million year time lapse video over the course of 10 minutes. All of a sudden at the end, it just stops. You see the explosion and it just stops. And it's like, oh, where's the black hole? It's like, the black hole is that little blip at the very end, right? It just
Wow.
instantly collapses on itself. And
So
yeah.
so once the mass or the force can no longer keep other mass from coming in. What was it again? Can you describe it one more time? I don't know if I fully understood the limit
Yeah.
of neutrons.
So basically at some point, the point of or what happens with the black hole is that the gravity is so strong that as objects are fusing together, and they were forming together, there's not enough energy that they can possibly have to ever escape the gravitational field. So imagine rockets escaping from Earth. It requires us, on one side of the equation, we have the velocity, and the other side, we have this gravitational constant, which this gravitational constant depends on how much mass. Imagine that the mass gets so big that this velocity here approaches the speed of light, right?
Okay.
The speed of
Okay.
light is a static thing, right? So on one side of the equation, you have a static number,
Oh.
and the other
Mm.
side, there's no limitation on mass. Mass can be as big as possible. So at some point, the mass is so high that not even light can escape. This is why it's a black hole.
Oh.
Photons are the carriers of light. They do have a very small mass, like almost infinitesimal, very small mass. But at some point, it's the gravitational field is so high that even, like, as light would try to go, like, around it, like, let's say light's coming around the side of it, it actually just gets sucked into it. And so there's actually this I believe it's called the Schwarzschild radius, and that's the point at which you can actually see light orbiting a planet, orbiting a black hole. It's a really
Oh wow.
interesting thing. If you were able to get that close to a black hole, you could see the back of your head.
That's similar to have you seen Interstellar?
Yes, it's a
The
great
I
movie.
think the
Yeah,
visuals there are pretty cool to visualize it because it's fascinating enough hearing you say it, but like seeing it too is remarkable.
yeah, and I think that's, the concepts they talk about in Interstellar really bring up some of the paradoxes, right? And that's that as you're really close to a black hole, because space-time is warped, you can imagine that light traveling in a straight line is going to travel at the same speed. Well, imagine, though, now that it's curved, light has to the distance is farther. Well,
Mm.
we know that velocity is distance over time. So in order for the equation, the limitation of the speed of light to still hold, which we know it does, then time gets dilated around a black hole.
Wow. So it is
It
in some ways, I guess, going back to what you mentioned about studying, like studying the Earth now in a normal state versus studying the extremes. Like the extremes, kind of, it does equations start to break down, or like just start to like just dissolve. How would you describe that?
it's not that they break down. We understand the concept of time dilation,
Okay.
and so we know that that happens. Again, in some ways, it's somewhat of a theoretical construct because we haven't, we haven't been able to observe a black hole. However, we have been able to observe time dilation. Even in smaller, it happens still in smaller gravitational objects. It's just, does it happen enough so that you have a measurement device that can tell the difference, right? You couldn't start a standard stopwatch and test it around the Earth because you don't have that sort of resolution. But we have run experiments to show that there is time dilation as a result of this, space-time warping around a large gravitational object.
Wow. So okay, so a black hole forms. Now, is it the fact like it just stays there in a certain part of the universe? Is it the fact that it eventually a black hole will draw all of the universe into itself if we had enough time? Like how does that work? Or where well, okay, let's start with that because I got one.
Well, that is an interesting question. Yeah. So I think the really interesting part of a black hole and what happens with gravity is the more gravity you have, the harder it's pulling on itself. And so again, after you've gotten past that neutron star limit, it's essentially it's a point. It's a single point in space, and you can define. There's I think is probably the Planck length is how they might define what the length is. Again, this is probably where I'm going to get corrected, but it's almost it's for our purposes, it's almost like, just consider it the smallest possible thing that you could ever imagine. Everything is down to that point. And so if
Okay.
all the gravity is there, then then in some ways it's the simplest possible physical object we can describe. It's really only got three identifying measurements, and that's what is its spin, what is its charge, and what is its mass. For something that is that large and being such a massive object, for you to be able to describe it in such a simple way, it's fascinating. And so, yeah, I guess so. There's a lot of theoretical research about what happens if two black holes are orbiting each other, specifically around what happens to time dilation, because when you have just a black hole, we know that the closer you get to it, the slower time goes. And so if you took, like, I guess an explanation for everyday world is, let's imagine you and I are traveling on the interstate, Josh, and there's a black hole on the left side of the highway. If I'm in the left lane and you're in the right lane, we're going to get to our location and you're going to be older than I am.
Because it took me
Right.
longer to get there.
Let's say we were the same age. Let's say when we left, let's say I'm being nice, I'm the same age as you.
Well, how about this? By the time we get there, I'm the same age as you.
You know, yes. Okay, that's probably a better way to say it. I'm older than Josh, and so
Just a couple years.
When we'd leave, I'm older, and when we'd get there, we would be the same age. Yeah, that's
so because it would take me longer, even though we're right beside each other, basically, because you're drawn in, and it's because basically it's a curve. Is that why?
Yeah, it's because essentially what's happened is if you look at the curvature of space-time, I would have actually, a straight interstate is probably not a great way to describe it, but imagine what we think is sort of like a path. We're in similar lanes going the same path. I've actually traveled, the distance that's been traveled has been longer. Therefore, time has to be shorter. It's limited by the speed of light. Again, I might be botching that a little bit. I hope that there would be some physicists that would correct me. But anyway,
I mean, is it?
Yeah.
Could I give another thought experiment? Maybe something like if you're climbing. I mean, if you take like a handicap ramp versus just stairs, like you end up at the same. Well, I don't even know if that's a good idea, or like a good example. But like a handicap ramp, you're going to get there, but it's going to take you a lot longer because you have you have a more gradual incline versus stairs. You can just go straight up and get there quicker. Is that in any way possible?
Wait,
Just because
sorry, repeat that to me again.
So, so let's say we have to get into an entrance, and you take the handicap ramp, which is just it's a gradual incline getting to the same place. I walk alongside it and then just go straight up the stairs and get there quicker. That's probably not a good example.
It is. It's just. Yeah. It's. Yeah. It is. It's a good example of like how longer paths take you longer to get there. And again, it just kind of it's sometimes it's tough to wrap your mind around. It's just that when you think about gravity distorting space and time around a massive object, you know, the concept of a straight line doesn't mean the same thing, because you're actually, if you're thinking about that trampoline, you're going down it. You're actually not going down a straight line. You're actually going down that curve on it. So
Okay.
anyway, let's talk about the. I like the idea of thinking about is it possible? Like maybe a better way to frame the question is the eventuality of the universe that it'll all get swallowed into a black hole?
And could you think of a black hole as like I don't know, as like an anchor in time and space, where it's like it just doesn't move anymore, or it still moves just like stars move and are drawn by other things?
It still moves because it's all
Hmm.
dictated by the attractive forces of gravity, right? Like that has an infinite range, and so black holes can orbit other
Oh,
black holes. They can orbit planets. You know, in some
wow.
ways, it kind of gets the idea of like, what does stationary mean, right? Like, how do you measure? It's all relative to something else, right? We don't have a way of like labeling a point in space-time. All we have is a way of labeling our reference frame. So this is a
Hmm.
big part of physics, is like, okay, well, we're this far away from a black hole, but we know that we're getting pushed to this side of the galaxy. It's getting pulled this direction. So all we can tell is sort of like relative. And so that's what we do, is we get all of these relative points in space in terms of stars, and make our best approximation for, well, what is the absolute difference in our distance? So black holes will get pulled and moved around. It's, you could think about them as saying, well, imagine a black hole was just a big object. Imagine you put in a sort of outline, and like you told kids, hey, don't cross this line. If you cross this line, you won't come back, right? Like that's, if you cross
I would immediately
that
cross the line.
radius,
I would immediately
don't
cross it.
cross the line. Oh yes, of course.
Keep going, keep going.
Interestingly enough, if you cross the line, for you, it would be almost instantaneous. You would just get pulled in to the black hole. But I would see you, and because of the time dilation, it would seem like you were going slower and slower and slower. And so it would take forever for me to see you get swallowed by a black hole, because of the way time
Wow.
slows down around a black hole.
Wow. But for me, is it speeding up?
For you, it's instantaneous. So, right. So this is
Yeah.
the idea
Yeah.
of like, for
Wow.
you, it's instantaneous. For me, I'm living my entire life. I would spend a good portion of my life watching you sit there and disappear.
That'd be a
I'm
boring
getting
life.
older, right? I come back years later. For you, it's instantaneous.
Yeah. Which is why you should cross the line, right? Because that's a boring life for you. Like, but I'm having more fun.
What happens in a black? Is it? Who knows?
Yeah, that's a fascinating. Okay, so yeah, those are two fascinating things. Maybe we can briefly kind of touch upon that. So one, what you mentioned about like would there ever be a black hole that then sucks in the entire universe in some way? Maybe black holes combine, and then what we just talked about there, like if that is also possible too.
Yeah, I'm not sure if there's an eventuality where everything gets pulled into a black hole, just because the universe is expanding at an expanding rate. If the universe weren't expanding, I would say that it seems natural that the eventuality is most things would get swallowed into a black hole. But the black hole's gravitational field, while it is infinite, it decreases as 1 over r, the distance squared. So the farther it is away, the black hole is less likely to pull on you. So I don't think that there's many eventualities in our current universe that everything ends up in a black hole.
Yeah, quick question. So I've never really understood this. What is the universe expanding into? Like what, I don't even, like, what is the edge? Like, what are the outer limits of the universe? Is it matter? Is it just like our thought process?
This is an excellent question. I am not even going to begin to understand. I do know that there's a really brilliant physicist by the name of Brian Greene who postulates, maybe like the Big Bang that happened that started all of this. Maybe this Big Bang is actually just happening inside of another type of universe, and there's a bunch of other Big Bangs. We're just living in one of those universes, and maybe they're all expanding, or maybe some of them are contracting. So the reality is we don't know, and I don't know that we'll ever know. In some ways, does it make sense to? I think, again, another analogy I heard, or I think I read in one of Brian Greene's books, is like, imagine that you want to know what's past the edge of the universe, and you say, okay, well, imagine you're on Earth, and you say, hey, I want to go north. Okay, so somebody keeps pointing you in a direction, and you keep walking in that direction, and eventually at the North Pole, and you ask somebody, like, hey, how do I go north? And they're like, that question doesn't make any sense, right? You can't get any more north, and so maybe that's the edge of the universe. Is there's nothing. It doesn't make sense to try to think about what's past there. Again, I'm obviously no expert on this.
Do they have any theories about what the edge of the universe looks like, or what it's what it's composed of? Or is time different out in the edge of the universe, or like, blows my mind. That's all. It's crazy. It's cool.
Yeah, I mean, they've talked about it containing some of the like fundamental particles that were around at the beginning of at the Big Bang, because they were essentially like pushed out, but a lot of those were just spread out in the universe. And so the edge of the like if you're on like the wave that's expanding into the edge of the universe, I'm not sure what is there, and I'm not familiar with theories that describe what is on that sort of like wave that is expanding out.
So like going back to the trampoline analogy, we'd have to picture like a constantly expanding trampoline as well in that case, like if it was the universe.
Yeah.
And then wouldn't that though have an effect on gravity itself, or on the gravitational bodies if the trampoline itself is expanding? Oh, fascinating. Okay.
Yeah, a good way to think about it is, imagine you take a big sponge and you push it into a tiny object, and so like when it's expanding, everything in it is always expanding at the same. It's not like we're all sitting here and then the edge is just moving out. It's everything is sort of all expanding out at the same time. So you're right, the gravitational fields also diminish as a function of time because the universe is constantly pulling us all out.
So so like the next time I gain 10 pounds, that could be my excuse. Like everything's just expanding. I have no option in this case.
Yeah. Either that, or we've been stuck inside in a pandemic eating potato chips too much.
That is for sure. Okay, so this has been fascinating. Next time, like you mentioned, we kind of want to get into the uncertainty principle and quantum mechanics. But yeah, so what's a couple ways that you think you can tie up this conversation and then kind of lead into the next one? Sorry, real quick, and maybe offer a couple questions that people can think about for the live one too.
Okay, so the questions, anything revolving around gravitational forces and black holes and these sort of paradoxes of what happens around a black hole, right? Like, can you take a cell phone into a black hole and call somebody and tell them what it looks like? Things like that. any question is open. I'm happy to speculate. If you want to correct us on anything, you're welcome to do that. And just anything about like the formation of these black holes and like how we experience gravity. I think those are all good questions to frame. So what we're going to discuss next time is the weirdness of quantum mechanics. Gravity, I feel like everyone has a reasonable handle on like what gravity does, and even the concept of a black hole, it's not that far fetched. I mean, there's a lot of weird implications, but quantum mechanics just has these insane things. As Josh said, the uncertainty principle, and that's that you can't infinitely know two characteristics of a particle. Like you can either know where it is or you can know how fast it is going, but you can't know both of them, right? Like why, right? Like can't you just like why can't you detect it? Like what happens? And so that's going to discuss quantum mechanics, which is something that Einstein just roundly rejected. First, he did not believe in it. Didn't make sense to him. And then when he finally did, we realized why he had such a tough time with it, because he had a tough time reconciling, gravity and quantum mechanics. And guess what? Still to this day, we don't have an understanding of it. But we have theories that try to tie this together, such as string theory, which is going to be our last podcast in this series.
Great. And I just realized we really didn't even get to singularity, but that's okay. I had enough. I have enough interesting things to think over now. Anyways,
well,
we'll get to that at some point.
A gravitational singularity is a black hole. That's what a singular. That's a singular. It's a singular. It's a point at which everything just collapses to a single. So that's the concept. A singularity, I guess, in principle, is just basically the point at which everything comes to a head and stops sort of at one point. We can think about it in many different ways, but in gravity, it's everything is down to a single point.
Okay, but you still need, like you said, you still need three things to describe this single point, right? So that still wouldn't, like the singularity, I still don't fully understand that, I guess, because like you can't ever have one thing to describe one thing, if that makes sense.
Yes.
It's as close as we'll get.
Think about but also think about how hard it is to describe a planet, right? A planet is, fractions. It's the thousandth the size of a black hole, even like tens of thousands the size of a black hole, and there's not an infinite number of ways, but there's a large number of variables it takes to describe a planet. But you can describe something supermassive with three characteristics.
So at least approaching a singularity, as close as you can get, perhaps.
Yes.
Like three is much simpler, obviously.
And honestly, for our purposes, honestly, the mass, it's kind of mainly characterized by the mass. The charge and the spin, obviously, we need to know because that dictates how the fundamental forces interact with it. But the fact that it's just its mass, and we know we don't have to describe radius or any sort of atmosphere or anything. It's just a mass. So that's fascinating.
Sure. Cool. All right. Well, yes, Lee, thank you so much. This has been really enlightening for me. I've enjoyed it. And yeah, looking forward to hearing questions from others, what other people think about it as well, and then further exploring more areas of this insane life that we all live. It is fascinating.
Don't forget to like our channels and join in for the YouTube Live. You can ridicule us. You can ask questions. You can harass us for something we got wrong. It's all open.
It's just going to be a roast then, if you want to do that, which is fine. Just roasting us.
We can curate the comments, right?
We'll censor. Yeah. But
right.
Yeah, okay, great. Looking forward to it, Lee. Thanks again.
Cool. Thanks so much.
Cool.
Bye.